Welcome you all to this course on defects in material. In the last few lectures, we have discussed at length on dislocations in FCC, BCC and HCP metals. But these metals which we have considered essentially are, we can say that they are disordered materials. But there are many materials which form ordered alloys or ordered compounds, or precipitates form in many of the materials which have disordered FCC structure, or there are cases where alloys undergo transformation from disordered to ordered state. In such cases, what is the sort of dislocations which will be responsible for deformation in the material? Let us have a brief discussion about that in this class. If you consider the best example is to take a two-dimensional lattice. The lattice which is being shown here is essentially a disordered lattice. Actually it is an alloy, you consider it to be alloy which contains of an atom A and B, which is in 50% A and 50% B, and the atoms are randomly distributed. So we cannot identify in which position A atom is occupying, which lattice position B atom is occupying. So that I had shown it by a gray color. In this, the shortest translation vector, essentially if you look at it, is what is being shown by this arrow. And what will be the magnitude of it? Magnitude of this vector essentially is of the order of A by 2, 110, 111. It will be in two-dimensional lattice. Generally in three-dimensional lattice, if you consider, it will be 110. And let us consider the case this alloy gets ordered. When ordering occurs, what is the way the ordering occurs? It is not that the ordering starts from one point and it spreads. Most of the time what happens in a sample, like if you consider a sample which is like this ordered nuclei may be occurring at different points like this. These ordered nuclei will grow and then join together. Then it will completely transform to the ordered phase. That is the case which we are considering here. We have two nuclei, we are considering it, where we have shown these two nuclei. In these nuclei, if we consider it, the translation vector for a perfect dislocation, or the translation vector in the disordered lattice, shortest translation vectors in this is A by 2, 111. This is the translation vector. When it is ordered, because how do we decide a translation vector? Because from one point to another point, if you displace an atom position, it goes from one position to another identical position. If we apply this criterion, then immediately we can see that from here to here is this vector is the Bajs vector of the ordered lattice, correct? That is the shortest translation vector. That is essentially A 111, or if we consider a three-dimensional lattice, it could be A 110, correct? If you consider a lattice with this Bajs vector, the self energy of dislocation is going to be very high. Because of this, it would prefer to exist in a condition where the self energy could be reduced. If that has to happen, then this should split into partials of the type A by 2, 110, that is two dislocations of the type A by 2 110, if it splits into it, okay, then what is going to happen is that the self energy of the dislocation is reduced. These dislocations can move together as one group, okay, and since both the dislocations have the same Burgess vector, they will repel each other, okay, and when they repel each other and they move away, a new interface is created, okay. That region is called as the antiphase region or the antiphase boundary, okay. This is one way to look at it, okay. Now, the same case where one nuclei has formed here, we will come back to it again with respect to some specific system. This is just to show that the dislocations can split into and these partials are called the super partials, okay. These things will come later, okay. When this dislocation, the two nuclei are formed, okay, when they grow and join together, what happens? Let us look at it. When these nuclei grow and join, they perfectly fit, okay. There is no interface or nothing is being created, okay. Now let us look at another case where exactly identical two nuclei are formed. These two nuclei grow and join together, then what happens? Now if we look at it, we can see that from this region to this region if we go, the atom positions have interchanged, okay. This boundary between these two regions are called as antiphase boundary, okay. If you look in this region, this is perfectly ordered. You look here also, this also is the same type of a structure, but when they join together at the interface, the atoms are not matching correctly, okay. If I move an atom from here to this position, okay, by this vector A by 2 1100, okay, when this is being moved, this will come back to a correct position. That means that this vector is called as the fault vector. So the fault vector of the antiphase boundary here is A by 2 111, okay. This is how the fault vector is defined, okay. Is it clear? So we have considered two cases. One, the perfect dislocation in the ordered lattice splitting into partial, okay. When that happens, this dislocation is called as super dislocation, okay. These dislocations, these two are called as super partials, okay. That is, you remember that when we talked about the FCC, the dislocations which form stacking faults, we call them as partial dislocations. The same terminology is being used. Here, these are called as super partials because these dislocations are perfect dislocations in the disordered lattice, but in the ordered lattice they create a fault. So they are called as super partials. Right. Now let us take some few specific examples of crystal structures. This is L12 structure. This is the structure in which the precipitates in many of the important nickel-based superalloys have. Okay. The stoichiometry of the compound is Ni3Al, where sometimes aluminum is replaced with partially with titanium or niobium and all these things, many elements. Okay. Here if you look at it, the aluminum occupies the corner positions, nickel occupies the face centers. Okay. This is the close pack plane here also is 1-on-1 plane. In this plane, if you look, what is the perfect translation vector? It is from going from here to here, or from here to here, or from here to here. Okay. In the disordered lattice, if you consider, half of it from here to here is essentially what it is going to be the translation vector in the disordered lattice. Okay. So, this super partial, as I mentioned, if we consider for A110, the Burgess vector, the B squared becomes 2A squared, correct? And for this dislocation A by 2, 110, this B squared becomes A squared by 2, right? So, if it splits into 2, that for both of them together it's only A squared, so there is a gain in energy. So, this reaction is always possible. Or as a general principle, any dislocation which tries to split into partial with smaller Burgess vectors, there is always a net gain in energy. It would prefer to go, then when there is a gain in energy, the material is now going to exist in a much more stable state, okay, provided that is possible. Okay. Here, when this sort of a separation takes place, these two dislocations have got the same Burgess vector, A by 2, 110 type of a Burgess vector. So, since the Burgess vector remains the same and they are in the same slip plane, as we have discussed earlier in a few classes back, these dislocations will repel each other. Okay. When they repel each other, when they start moving, there is an antiphase boundary which is being created. That means that an atom here, if we consider it, the atom in the next layer is being put here. Okay. It is being moved from this position to another position, where if you consider here, it has one unlike neighbor and here two like neighbors are there, which shifts to all the three of the same type of a neighbor. That means that bonds are changing. If the bonds change, that means some new interface is created. Okay. That requires some energy. Okay. So, antiphase boundary is created. So, depending upon the antiphase boundary energy of the material, that will decide what is going to be the separation between the two partials. Okay. This can be also considered in a different way. The way in which we can perceive this is that one dislocation with a Burgess vector A110, it splits into two dislocations with Burgess vector A by 2, 110. Okay. These dislocations assume that they have the same Burgess vector, okay, both of them, they repel each other. So, when they repel each other, assume that this dislocation is, they will separate. Okay. When this dislocation moves, assume that R in this configuration, when they have reached an equilibrium separation, we apply an external stress. When we apply an external stress, what is going to happen is that the stress is in this direction. This dislocation will try to move in this direction. When this dislocation moves in this direction, it is in an ordered lattice, it is there. So, it has to create the first dislocation which it moves atoms from this position to this position. That means it's a disorder has to be created. So, extra energy is required for the dislocation to move. Okay. Because as it creates, it has to create an interface also, not only just the movement. When the second dislocation comes, it moves in a region which is already disordered, right? It requires less stress to move, so it will come quickly close to this dislocation, but then it finds that the repulsion between the dislocations will start acting, and then it will just repel it. So, they try to maintain an equilibrium separation, which is dictated by this antiphase boundary energy. Essentially, the repulsive force can be equated to the antiphase boundary energy. Okay? Multiplied by the distance will give the force. This way we can find out what should be the, if we can measure the separation between these two dislocations, we can get some idea about the antiphase boundary energy. Okay? In that structure which we considered, all dislocations are like here. If we look, all these dislocations are super partials, correct? Super dislocations. This is another structure which we consider, which is L10 structure. This is gamma TAAL. Okay, there are copper, gold 50 atom percentage, There are many alloys which go into this sort of a structure. Okay. Here it is like an FCC lattice. This layer is consisting of one type of an atom. The next layer consists of another type of an atom. This consists of the same type of an atom. So, it is like a layered structure. Each layer consisting of a particular type of atom along the C direction, they are stacked in an AB type of a stacking sequence. Okay. When such a type of a stacking sequence is present, let us look at in this one also the close packed plane. If I look at it, okay, this is the way it appears. Okay. This structure, for all practical purposes, if you assume that the atoms we can't identify which position they occupy, it is like an FCC structure. So, this is the close packed plane. Here now if we look at it from here to here, the Burgess vector turns out to be the same as the Burgess vector in the disordered lattice. Whereas, and from here to here also it is in the disordered lattice, but from here to here this dislocation is a super dislocation, which is essentially double that of B1 in magnitude. Okay. That can still split into partials. So, in some of the structures, depending upon the crystal structure, okay, in some of them, in some direction, because 12 slip systems are there, some slip system, it is essentially the perfect dislocation of the disordered lattice which moves in this. In another slip system, slip plane, if you look at slip direction, if you look at it, it is the ordered one, so it will split into partial, creating a super partial, creating an antiphase boundary region between them. Okay. So, this is one way it can happen, because I am just trying to give you a flavor of what all the types of dislocation reactions which are possible in ordered lattice. Let us consider a third case. Okay. With this case, we will stop talking about these ordered lattices. Here, if you look at it, this is a structure where the C by A ratio is 2. This is equivalent to 2 FCC lattices if we keep one on top of the other. Okay. And the atoms are arranged at specific positions. Okay. A type of an atom, that is, suppose we assume that the stoichiometry will be AB3 type. A atoms occupy all the corners and the center. The B atoms occupy all the faces and the edge here. Okay. In this lattice, if you look at the close packed plane with respect to FCC, if we talk about it, FCC indices, this is a 1-on-1 type of a plane. This is how the arrangement of atoms are. Okay. The red atoms show the atom on the next plane. Okay. Why I am talking about this particular structure is that in many nickel based alloys like alloy 718, alloy 625, okay, or many other alloys are precipitates form with this type of a crystal structure, not gamma prime with this called as gamma double prime in the superalloy terminology which is used, these precipitates form. Okay. Here again if you look at it, if we go from here to here, this is the perfect translation vector in the ordered lattice. This is in this direction, which is essentially nothing but 1 bar 0. Now let us look at in this direction or in this direction. In these two directions, from this position to this position, only that this translation vector tells that if we move from here to here only we reach a perfect identical position. That means that perfect translation vector now turns out to be twice 0 1 bar 0. Okay. That is essentially in one case it is A 1 1 bar 0, another case it is twice A 101 bar 011 bar. Okay. That is in these two directions the Burgess vector of the dislocation is extremely large. For all these dislocations will try because to split into partials. So when that happens, the super partials in this direction is going to be two dislocations two superpartials will have to move. In these directions, 4 superpartials they will split into. That means that when all the 4 that is in the direction, in this particular direction, when 2 dislocations have passed through the region, okay, that is in this particular, this is the one direction in which this dislocation is moving, 2 partials are there. In this region as well as in this region, it is perfectly ordered. APB is between them. First dislocation creates an APB, the second dislocation, okay, that it removes it, so that is how it moves. Now the same thing when it has to happen in a direction like this, which is the slip direction is in this direction. Now we should have 4 dislocations should be there, should pass, go through it, okay. After all the 4 dislocations have passed through it, only we will find that ordering is perfect ordered in this region, perfect ordering is going to be there. In between region, there is antiphase boundary is going to be created. This is clear? Okay. So, essentially, generally people say that whenever in any material ordering is there, if we see pairs of dislocation, we say that ordering is there. That is not correct, because that depends upon the crystal structure. This is one example where in this direction 4 dislocations. That means essentially what we should look at is if groups of dislocations pass through some region, okay, and the number of dislocations is dictated by the Burgess vector of the superpartial, a Burgess vector of the super dislocation, and that of the superpartials which they formed, that decides how many. In the case of gamma prime case, in many of the superalloys, 2 dislocations are good enough. People, that everybody extrapolates it and tells that okay, that is good enough. So if you see 2 dislocations, ordering is there. That is not the case. Depending upon the specific system, in some cases it could be 2 are good enough. Here what happens is that in this direction, if 2 dislocations pass through, order is not completely restored. You require 4. Okay. This is perfectly all right. Okay. Now, having talked about these various types of, so what we have considered is we have considered 3 cases. One case only superpartials are formed, okay, which splits into partial. Another type of a structure where we can have a superpartial as well as a perfect dislocation of the desired lattice can be present. There is a third case where we are seeing that the superpartial itself can have different types of different magnitude. Depending upon that, the number of superpartials which are required to pass through the lattice to restore order can turn out to be more than 2. Okay. This is here what I have tried to do. It is the same structure which I have considered and showing that this same crystal structure, okay, this we considered in an ordered lattice if dislocations are present, okay, what is the type of dislocations could be there, super dislocations, and the same structure, like if you remember how we defined that APB in a 2-dimensional lattice, okay. This is also, this precipitate forms in many cases like nickel 3 vanadium, okay, Al3Ta, there are many systems, okay. That is stoichiometric composition of nickel 3 vanadium or Al3Ta. In this case also, the crystal structure is DO22. When we EH at below the order temperature, the nuclei of the ordered phase form, they grow, and when they grow, some cases they will join together without creating a fault. Some cases when they join together, they will be creating, okay, antiphase boundaries. Okay. What are the types of antiphase boundaries which form is being shown. Depending upon the way they shift between them, I mentioned earlier how to define the antiphase boundary vector. Depending upon that, we can see that between this boundary here, this is one type of a structure. This is the same Burgess vector in a different direction. It creates another type of a structure. This is as again creating a third type of a structure. Okay. All these structures which we are seeing now is essentially nothing but, okay, structure of another phase. like in a stacking fault FCC, okay, stacking fault creates HCP structure. Similarly, antiphase boundary also, because it is a superpartial which pass through, they will create a fault. The faulted region could correspond to a nuclei or the unit cell of another structure. That is what typically which we can see in these cases, where it is a two-dimensional projection of the 3D lattice is being shown. This is shown along 100 direction projection. Okay? Okay, having talked so much about it, now let us go back to dislocation interaction. This dislocation interaction we have discussed earlier. Okay? What we said is that when dislocations of the having Burgess vectors which are opposite to each other are the same Burgess vector, but the line sends which are opposite to each other, when they come, they will be attractive. Okay? As we mentioned, if the dislocations have the same Burgess vector, they will repel each other. Okay? This we considered with respect to dislocations in the same slip line. Suppose we consider a dislocation one dislocation is moving in this plane. In real material, what will happen is that another dislocation is moving in this direction, and this is moving down, this is moving in this direction. When they, and it can so happen that these dislocations, okay, the Burgess vector is such that the force can be a repulsive force. They may not attract, but under the action of applied force, okay, since they have to move across, they will try to cut through this precipitate. Okay. These are all the cases which we have considered, and what is the consequence of it. Let us look at it. Here we have one dislocation. Here we have considered the case where the slip lines are perpendicular to each other. Okay. There is one dislocation here with a Burgess vector in this direction. In this slip line, perpendicular slip line, there is a dislocation with a Burgess vector in this direction. These two dislocations, when they pass through each other, okay, what has essentially has happened is that this dislocation has a Burgess vector in this direction. As it cuts through it, it will create a stub. So this is the one stub, an atomic stub will be created, which will be equivalent to the Burgess vector, because that has to move the atoms on this plane. Okay, when this dislocation passes through this region, it has to move all the atoms in this plane by that vector, it should shift it. So the dislocation line would have shifted here. So this is how now the dislocation looks like. A step is created, and the step creation means that there is an increase in length of the dislocation. This way, as the dislocations interact, the length of the dislocations can increase. So this also leads to multiplication of dislocation. Okay. And let us look at this particular one. In this case, when this dislocation cuts through the dislocation in the horizontal plane cuts through the dislocation in the vertical plane, okay, since the Burgess vector of this dislocation is in the same direction, okay, it will not create a stub, because the stub which is creating in the same direction as it. Okay. So essentially, a step is created only in this dislocation, but not in this dislocation. Okay. And if we look at what is the plane in which this step is lying, okay, this is the line direction. The Burgess vector of this dislocation is all in this direction. Here also the Burgess vector in this direction where the arrow is being shown. That means that it is a edge character, but lying out of the slip line. Okay. And when we know this is the line direction and this is the Burgess vector and they are perpendicular to each other, the slip line is this plane, the step itself is the slip line. If we apply a stress in this direction, all the dislocations will be moving in the same plane only, in their slip plane, so they can easily move. So this type of a dislocation which is created, which is not in the same original slip plane in which it is moves, we call them as jog. The terminology which we used to describe them is, they are called as jogs. So jogs are created, but the jogs which are created in an edge dislocation, it is able to move easily under the action of an applied stress. Okay. Let us look at another case. This is also the same. type, but only thing is that the bias vector of the dislocation has changed now. This is the line direction and the bias vector is in this same. So, both the dislocations lying in two perpendicular slip planes, but the bias vector is in the same direction. Here what happens is that when this dislocation is being cut by this dislocation, since the bias vector is in this direction, it will create a step here like this. Okay, one step is created in this. In this also a step is created. Both the dislocations steps are created. Okay. And if we look here, this is the direction of the bias vector, correct? And the line direction is also in the same direction. Okay. It is a screw component. Okay. Here again, if we look at it, this is the line direction, okay, for this segment, and bias vector in this, it's a screw component. Okay. And if you look at this one, this stub is all lying in the slip plane only. When the stub lies in the slip plane, we call them as kinks. Okay. So, they have screw character and they are kinks. Okay. And since they are all lying in the same slip plane, if you apply a stress, they will move easily. So, that means that whether a jog or a kink is created in an edge dislocation, under the application of a stress they are able to move easily. Okay. Let us consider the case of screw dislocations, intersection of screw dislocations. Okay. Here we are considering one screw dislocation with a bias vector in this direction, another screw dislocation with a bias vector in this direction. When they cross each other, okay, since the bias vector of this dislocation is in this direction, as it cuts through this dislocation, it will create a step in this one. This water step is created. This dislocation, when it has cut through this particular one, since it is in this direction, a step is created in the upward direction. Okay. If you look at this step, okay, this is the slip plane. Okay. This is also the parallel slip plane. It is out of the slip plane. Okay. So that means that it is a jog, and the bias vector is in this direction. That is, the bias vector is in this direction, the line direction in this direction, they are perpendicular to each other. So, it is an edge dislocation. Okay. And the slip plane of this dislocation is going to be in this direction, and when we apply a stress like this one will try to move, okay, either in this direction, okay, but slip plane for the extra segment is going to be in this plane. So, it will try to move in the opposite direction, which is not possible. So, being pulled in different directions. So, the jog which is created, it is not able to move easily under the application of a stress. Okay. That means that the screw dislocation on both the segments, on two slip planes, adjacent slip planes, they move, but the jog will move. Higher stress is required to make the jog move. Okay. Now, let us look at the case, how does the jog move? Okay. We saw that there is a jog. The jog is lying in a plane, because if the stress is applied in this direction and if the dislocation is going to lie in this slip plane, okay, these two are perpendicular to each other. That means that in the case of a edge dislocation, when stress and the dislocation line directions are perpendicular to each other, actually the stress will not have any effect. So, the dislocation need not move, correct? So, if these dislocations have to move, they can move only by climb, the force which it can act. That is precisely what, because here this is a case where these are all the jogs which are created in a screw dislocation. We are applying a stress maybe in this direction, which applies a force in this direction, which makes the dislocation move. So, this dislocation has bent, because this is like something which is holding on to a dislocation. This is which is holding the dislocation from moving. So, the ends are as if they are pinned, this gets bent, okay, and this is the state of affairs. If this whole dislocation has to move up, what should happen? This segment also should go up, climb, correct? So, if a climb process takes place, okay, either interstitials are emitted or vacancies are emitted from that region. Okay. Here that is what essentially happens is that when this goes up, we are considering the case where vacancies are emitted. Okay. That means that a screw dislocation, when they interact, they create a jog. The jog to move, we require a very high stress. Though the increase in segment of the dislocation line is very small, but the stress which is required to make this dislocation moves is very high. So the jogs have an important role to decide the strength of the material. Okay. So this is one way in which it can go. Here if you look at what is the step which is being created, this step is only of an atomic step which we are considering it. It can so happen that the many dislocations have cut through, so the steps could be very large. Okay. In this itself, if you look at it, we will just try to draw this diagram itself and let us see how it looks. Okay. This is the line direction. Okay. You can consider it. And then if this segment bends like this segment is always caught here, and then this segment again bends like this. So what is going to happen is that if we consider here and here, okay, the dislocation line sense is in different direction, but the bias vector is in the same direction. Okay, they are of opposite type. So under the action of the stress, what can happen is that this can move quite high. This is stuck in this region. So we will have one region has come like this, another region has gone up like this. This is how this sort of dislocations with the same bias vector and different line sensor means that this we call it as a dipole. Okay. So this sort of reaction can happen where dipoles can be created. This is one possible reaction with which it can happen. So for the, depending upon the size of the jog, in some, when the size of jog is unit bias vector or unit translation vector in that direction, then vacancies can be created. If they are slightly larger than that, it's so possible that jog could be created. When more than one unit translation vector is there, that type of jogs are, the terminology which is used is they are called as super jogs. Okay. This is one case. There is another case which it can happen is that one region is like this, another region is like this, the dislocations are there. These two are in the slip plane and this is out of the plane, very large. Depending upon the local stresses, bending could, in one of them, the bending could take place in this direction, another, the bending, this could bend in this direction, correct? There are all types of reactions which can occur in these dislocations. So various ways in which, okay, the jogs, that is the, finally if the jog has to move, okay, it has to generate dislocation, there is either vacancies or interstitials and move. But when the jogs are not moving, they can, and they are held, okay, the stress is not sufficient to make them move, then what's going to happen is that dipoles could be created and many other shapes in which the dislocations could expand. Okay. Then, so we talked about two types of this one, jogs and kinks, and the kinks which form due to interaction between dislocations. Okay. And even in equilibrium cases, okay, a mixed dislocation, okay, is the state in which the dislocation remains, okay, the line direction, is it in a stable equilibrium condition? This is important when we consider a crystalline material. This aspect we will look at it now. Okay. How it happens? Generally, when we look at let us consider the case of an edge dislocation. This is how we see that the lattice planes are there, correct? And then this is the slip plane, above which an extra plane is there, correct? If a dislocation moves, then what will happen is that by one step, if okay. In this case, if a dislocation has to move from here, because atoms are going to be there on this slip plane, here atoms are going to be there on this plane, okay. Under the action of the stress, suppose this plane is being pushed a little bit, then this distance will become short and this distance will increase. So that is how this layer gets connected. This can be considered as equivalent to when an extra plane remains in this position, it is equidistant from these two. That means that is in an equilibrium position. If it has to move from this position to reach this position, it has to reach a position intermediate where this plane has to come on top of this one, correct? That position, it will have a higher energy. That means that if we look at the core of the dislocation, as a function of distance, if we look at it, energy wise, it will be like it's a minimum. Like this is how the energy of is going to change. So if this extra plane, okay, which is the line direction of the dislocation, I will just draw like this. This is the dashed line, is the dislocation line. If it lies between these two, it is in an equilibrium position. When it has to go from here to reach this position, it has to go through a high energy barrier, correct? This will be seen, okay, prominently in the case of covalent bonded material or ionic materials, where the directionality of bonding is going to be there. Now, let us consider a case, okay, where the dislocation line is like this. That means that this is a Burgess vector is in this direction, this is the line direction. Now, the dislocation is lying in a region that is higher energy and lower energy. If you look at the energy of the dislocation, the core is going to vary, okay. So it's not in a minimum low energy configuration. What is the way in which it can assume a low energy configuration is that if it part remains like this, there is a step is created, comes like this, another step is created. So minimum part of the dislocation line only has to be in the high energy region. Then if its step is created like this, if it moves, this is equivalent to this one. And all these are nothing but a kink in the slip plane. So this way also kinks could be created, because the dislocation line would try to remain in a position which is overall there, it is in a low energy position. Okay. This can be prominently seen in many ordered alloys or in that means that the long length of the dislocation line will be seen, either an edge or a screw type, mixed type of lines, if it is there. Okay. Wherever it is possible, it try to minimize the energy, and just like that dislocation line will be there like this, maybe it will be moving like this. This is how we will be observing the dislocation line. Okay. So, this is another form in which kinks could be generated. Okay. Now, so far we talked about dislocation interaction, and we said that in this sort of dislocation interaction, there is a slight increase in length of the dislocation is taking place, okay, and this gives rise to some multiplication, but the increase in length is very small. But generally we had seen that when we deform a sample, okay, the dislocation density goes from maybe 10 to the power of 4 to 10 to the power of 6 times, orders of magnitude, not 6 times, 10 to the power of 4 to 10 to the power of 6 times it increases, correct? Not 6 times it is increasing. So, that sort of an increase in dislocation density takes place. So, it cannot be accounted for the small steps which are created. What could be the reason for this? That means that there should be some sources which should be operating within the material, correct, which is responsible for such a high increase in dislocation density. Okay. What are the sources which we can think of? One of the sources which has been put forward is the Frank-Reed source. Okay. Here what is being assumed is that a dislocation line is there, a segment of the dislocation line, that is the BC, is in the slip plane, and AB and CD are out of the slip plane. If we apply a Burgess vector is in this direction, if we apply a stress, what is it going to, this is being pinned, under the action of the stress the dislocation triangle will like to bend, correct? So essentially when the dislocation lines are pinned between these two regions, it is initially straight. Under the action of a stress applied in this direction, the dislocation lines bends like this. Initially the forces are all going to act in this direction, because we have studied that the force is perpendicular to the line direction everywhere, and now the force is going to act in this way, correct? As the dislocation line bends and reaches a critical value, a semicircle, okay, now the force is going to act here like this. In this one it will be in this direction, here it will be in this direction. So, it will make the dislocation expand, because this is the pinning center, it will try to expand. This expansion is what it will give rise to this particular type of a shape which is shown in C in the figure. Okay. So, this will make it in the third case, this will be bent like this, but still the forces are going to, here force will be act in this direction, here force will act in this direction, it will expand further and further, and at some stage these two with line direction in opposite sense, same Burgess vector, when they join they will attract each other and they will join. When they join together they will break and this will form a circle, and this region is again joined together. So, this case, if we consider it, that is a critical okay. You consider that they have just joined together. When they just join together, the stage which will reach these two, they join together, they annihilate. So, this is a one which is a length like this, that will try to shorten the length and reach this position. Here you have one dislocation line, that is one dislocation loop which has been generated, shear loop. Okay. Since the stress is being applied continuously, loop after loop can be generated. So, this source is called as a Frank-Reed source. Okay. In many crystals it has been seen experimentally also, in situ electron doing in situ electron microscopy, one can observe, one has observed this type of sources operating in the sample. And all these dislocations like this, when they form, these are all moving in the same slip plane, correct? because in the same slip plane it is being generated and they expand and go, that is one. And another is what is the critical stress which will be required. That stress is essentially we know that when a dislocation is being bent into an arc, the stress which is required tau equals T by B into R. This I think if you remember, this is the expression which is being used. Now R will become 2L, R will become L by 2, okay. T is alpha mu B square. So if we substitute this, we will get the expression 2 alpha mu B by L, correct? That is what the expression which is being given here, okay. From this it is clear that what is the critical stress which is required for a Frank grid source to operate, okay. There are many mechanisms by which these sources one can think of. One is called as if a dislocation is moving in a slip plane, okay. Assume that a screw dislocation is moving in a slip plane. This screw dislocation, it sees an obstacle in its movement in some region, then it cross slips onto another plane, okay. And then when it cross slips onto a plane, it finds that there is no obstruction, then it can again do another cross slip and come back to original slip plane. That is not the original, parallel to original slip plane, and it can move in these. Now these two ends can act as essentially a pinning centers. The stress is less in this for the dislocation to move. This can again act like a Frank grid source and generate dislocation loops, okay. This is found to be one of the main way in which more and more dislocations could be generated in the material very easily. Like if you think of FCC, there are 4 slip planes are there, 3 slip directions, so 12 slip systems. So 12 types of Frank grid sources could operate in all these planes, okay, and they could be generating dislocations when we are deforming the sample with small stress which is being applied. So these dislocations which are generated in all these planes, they will be interacting with each other as they move, okay. That is how the dislocation multiplication occurs. Not only that, these dislocations can interact amongst each other in the case of FCC or in BCC or in HCP. We have looked at what all the types of interactions which are possible. All these things we have looked at it, okay, in the last few classes. Okay. This process by which the source is generated is called a double cross slip process. And what are the other ways in which dislocations could be generated? Grain boundary is a sink for dislocation. Similarly, it can be a source also, from there it could be generated. When cracks are being generated, ahead of the crack tip, okay, dislocations could be generated. That could act as a source. In fracture mechanics, people look at these aspects of it, okay. Then simple case, if we take a sample, heat it to high temperature and quench it. The thermal stresses are there. The thermal stresses are relieved by punching out dislocations in the material. They could also act as source of dislocations generation in the sample, okay. Here what we have done is that when dislocations of these types are generated, okay, this is the sort of, yeah, suppose there is a boundary which is going to be there, okay. Assume this is a grain boundary. So when these dislocations reach this grain boundary, okay, the grain boundary will stop them, okay. That means that in the same slip plane there are dislocations one after the other, behind one another dislocation like this is there. That same arrangement which is being shown here with the dislocation line here perpendicular to a screen or coming out of that screen, okay. When this sort of arrangement of dislocations are going to be there, What is interesting is that all the dislocations have the same Burgess vector. Some stress is being applied. Okay. When that is being done, if you look at each of this dislocation, because they are like type, it will apply a stress on it. It is a repulsive force. This dislocation again will apply a repulsive force on this, correct? All the dislocations are going to apply some repulsive force, but this dislocation will repel not only this, it will repel this also. So, we can write an expression for the repulsive force between all the various dislocations, and the net sum of this should be balanced by the applied stress, applied force, that is minus sigma b. This is what the expression is. Another feature which becomes very prominent is that if this is solved, what is going to be the stress which is going to be on this dislocation? From here to here to each of these dislocation apply some repulsive stress. So, the stress multiplies. The solution to this is, on the average, if n dislocations are there, okay, n times sigma could be the stress which is going to be there and the dislocation ahead of it. When such stresses are acting on the dislocation which is closer to the boundary, a few processes which can happen is that the stress is so high that this stress can be relieved either by generating some dislocations on this side, so that the stress will be relieved and they can move, or if that is not possible, it can create a crack, because once we create a crack at the boundary, then the stress is relieved completely. This is how when we deform a sample, quite often one can notice that all depends upon the what is the stress which is required to generate a crack, okay, within the sample or at the boundary. Okay, we are considering a case of a boundary where the two possibilities are there. One, it can generate dislocation on the other side of it, other grain, and relieve the stress, or a crack could be generated. Okay. Then also that material failure will start. This is one of the way in which a failure could be initiated from the grain boundaries. Okay. Especially it has been seen that when these sort of boundaries contain some precipitates which are going to be there, which are very hard, then it's possible that it's getting elastically strained, okay, and many of the ordered precipitates like oxides and all, it's very difficult for dislocations to move. When the stress reaches a value which is equal to theoretical strength, the stress concentration on this dislocation, it will generate a crack in that. That has also been observed. Okay. Looking at the samples in electron microscopy, one can see a planar arrangement of dislocations and come and meeting at a particle, and one can see that a small crack has been generated in the particle. Okay. That means that in a planar arrangement, okay, all dislocations, okay, lead to increase in stress which is going to act on the dislocation which is closest to the boundary. Okay. So, essentially now what we have done is that we have looked at the various types of dislocation interaction and dislocation multiplication, also what are the types of sources which can operate. When these sort of sources are operating, especially because when this planar arrangement will take place, especially when the applied stress is low and only one slip system is activated, then this sort of reaction or when the stacking fault energy is low, then the dislocations are confined to move in only one particular slip plane, then planar arrangement of dislocation will occur in the material. In such cases, okay, lot of stress concentration can build up. Like we take in the case of aluminum where the stacking fault energy is high, cross slip of dislocations can take place also to generate that stress. Here if this is an edge one, none of them can cross slip also. That is how a build-up of stress will occur in the sample. Okay. So, we will stop here.